All right, so Thermochem is pretty much a unit about energy. Okay, so energy is defined as the capacity to do work or transfer heat. In terms of AP Chem, you can kind of think of it pretty much exclusively as heat. We don't talk too much about the work. I'll talk about it a little bit right now, but most of the energy stuff we talk about is going to be talking about heat. Okay, so this is an example of kinetic energy. We saw it at the end of last unit with the gases, right? We talked about how energy is dependent on the mass and the velocity of something. We're going to skip these problems. And then there's also something called potential energy, which we are going to talk about. So kinetic energy is the energy based on motion. Potential energy is basically the stored energy, so the potential energy that an object has access to. So easy way to think about it in everyday life is if you're on a bike on the top of a hill, you have very high potential energy because, right, you can potentially move down. And as you go down the hill, you have kinetic energy that increases, but you lose potential energy because you're going down in terms of elevation. So that's an easy example of potential energy. It's stored energy. Now, for Chem, we're not going to be talking about this. This is more physics. The potential energy that we do care about is something called electrostatic potential energy. Okay, and this is going to actually come up on the AP, or it might come up on the AP test. But I want you guys to write this equation down. I believe it's on your AP equation sheet, but you don't need to pull that out. I'm going to kind of talk about what this equation is, what all the variables stand for, what it means. It's actually pretty easy to understand, but just jot it down for now, and then we'll talk about how to interpret it. All right, so let's talk about this equation. So electrostatic potential energy is basically us trying to figure out if two objects are going to be attracted to each other or they're going to repel one another, okay? And this E right here, this energy, basically tells us that. Now, if this is a negative number or a negative value, that means it's going to attract. Okay, I know it kind of seems backwards, right? But negative means it's going to attract, and if this is positive, it's going to repel. Okay? So negative E is going to be attraction, positive E is going to be repulsion. All right, this K right here is a constant. It's going to be on your equation sheet, so you don't need to memorize. Just know the K is a constant. Now, the key thing to remember are these Q's. Okay, these Q's have to do with the electrical charge of the two objects that you are looking at. Okay, so they could either be a positive number or a negative number. Okay, and the D right here is going to tell you distance, so the distance between the two objects. All right, now the reason why negative means attraction is because systems in nature want to go to the lowest energy state. Okay, and so the lower the energy state, the better it's going to be. So if two objects, by getting closer, can lower the energy of a system, that's why they're going to attract to each other, because it makes it more negative. Okay, now everything else right here, it's pretty self-explanatory. This has to do with either positive or negative. So we'll be looking at things like protons, electrons. We'll be looking at things like cations and anions. And then the distance just tells you if something is far away from each other, how that affects the attraction and repulsion. Okay, so we're going to do 6.2 and 6.3, or I'll do 6.2, and then we'll try 6.3 on your own. But this is how we can use this equation to kind of demonstrate and prove some of the things that we already know. So we're going to use this equation right here, and the question is asking how we're going to prove how like charges, how their interaction changes with distance. Okay, so we're going to have two like charges. So we're going to write E. We're going to write equals K. And we have two objects that have like charges. So you can do positive, positive, or negative, negative. Doesn't really matter, but I'm going to do positive, positive. So positive times positive. Okay, and we're going to set it over some sort of distance. All right, so if we simplified this value out, we would get K over D. Okay, so this is the first scenario we're looking at. If we have two positive charges, at a certain distance d, the energy is going to be K and D. Now, KD, is this positive or negative? Yeah, this is a positive value, right? So since this is positive, is this attraction or repulsion? Repulsion. Good. Okay, which makes sense, right? We know that like charges repel one another, right? If you ever had two magnets and you try to put the two positive sides together, they push each other away, right? That's what this equation is demonstrating. If you have two positives, and if you did negative, negative, you would get a positive number again because they cancel out. That's what this equation is proving. All right. Now, the question is asking, how does it change with distance? So we're going to do the exact same thing. I'll do a different color. But this time, we're going to change the distance. Okay, so K, we're going to do positive, positive. But this time, let's double the distance. Okay, so 2D. Okay, now if we simplify this out, we would get K, but this time over 2D. Okay, yeah. So this is still a positive value, right? So it's going to repel, so this is positive. So it's still going to be repulsion. However, let's compare these two values, K over D and K over 2D. Which one is smaller?
K over 2D.
K over 2D, yeah, because you're having it, right? So this is a smaller value. So I'm going to write that it is a smaller value. If the value is smaller, that means it is less repulsion. Okay, which makes sense, right? Because if you have two magnets and you put them further away from each other, the repulsion is going to be less because the distance is increasing. Okay, and that's pretty much what we're using this equation to prove. Okay, now the reason why we're doing this is because sometimes on the AP test we get questions with no numbers. They give you an equation and they ask you to just prove something without giving you any specific numbers. And that's why I wanted to get you guys exposed to doing this. Sometimes you'll have to use just the equation, no numbers given to prove a point. And that's pretty much what we're doing here. Okay, make sense? All right, so let's do, so the conclusion here is basically the further the distance, the less the repulsion. Okay. So I'm going to have you guys do the same thing for 6-3. Okay, this time you're doing it with opposite charges, and you're going to demonstrate how the interaction changes with distance. So try 6-3. Same thing that we did, just try to prove it, write a quick conclusion, and then we'll move on to the next topic. All right, guys, so I have the proofs for you up there. Okay, you put an opposite charge, so a positive and a negative charge, which are opposite from one another. You get a negative E value, which means attraction, which makes sense, right? A positive and negative side of a magnet are attracted to one another. But if you increase the distance, the value is going to get smaller, and so less attraction as distance increases, which makes a lot of sense. Okay. As. AS.
What A? In what world is an A?
My goodness, this handwriting critique. Happy?
Yeah, thanks.
Okay. I want to write this, but oops, that was recorded. Anyway, all right, so that's basically just talking about how different charges are going to give you a different positive or negative sign depending on this equation. Might show up on the AP test, might not, but just want to go over it just in case because it does come up sometimes. All right, so let's get into the actual stuff that'll be helpful for the actual chemistry stuff. So we're going to be talking about energy, and energy is typically measured in AP Chem with the units of measurement joules. Okay, joules. Okay, and then we also have the variations of joules like kilojoules. These are the two most common. However, these are the other ones that are common as well. So joules is this unit of measurement. It's a combined unit of measurement. And then 1,000 joules is equal to 1 kilojoule, so kJ. Sometimes they also use something called a calorie, right? 4.184 joules. And then 1,000 little c calories is equal to 1 big C calories. The calories on our food labels is this one, though, not the small one. Okay, so just keep that in mind. So the 4 units of measurement for energy are joules, kilojoules, small c calories, and big C calories. Okay. Sometimes they call this big C calorie a kilocalorie, which I think is a better term because it tells you that it's 1,000 small c calories. But you might see those variations. Okay, so just a heads up. Those are the units of measurement. That's how we measure energy.
Will we be able to measure how many calories are in foods?
Yes. Okay, so whenever you are talking about energy, we always need to identify something called the system and the surroundings. Okay, the system is really easy. It's basically what are you looking at. 99% of the time when we use it in chemistry, it's where the reaction is taking place. That's going to be the system. Okay, so when we have a chemical equation, that's our system. The reaction is the system. And the surroundings is everything surrounding it. Okay? We always need to identify those two things because if we don't, we can't really describe where the energy is moving to and away from. So we always need to define those two things. All right, so a couple things. There are 3 different types of systems, and this might show up on the AP test. I'm not too sure. It doesn't show up too often. It's not going to be on our test, so if you want to ditch something, you can ditch this. The first type of system is called an open system. It's where matter and energy can be exchanged freely with the surroundings. So I like to use coffee as a good example of it. So if you have a coffee mug with the lid open, right, energy and matter can go in and out, right? So the gas molecules that come from the steam from the coffee, they can leave. If a bird poops in your coffee, it can go in. The energy, the heat can leave as well. So matter and energy can leave the open coffee cup very easily. That's an open system. Okay, so open system, good example is a coffee cup with the lid off. All right, a closed system would be the same thing, but this time you got a lid on top of it. Okay, because if you have a lid on top of it, the energy can leave, right? So the heat, eventually the coffee will cool down. But since there's a top on it and it's closed, like the air molecules can't get out, stuff can't get in. So the closed system would be like a mug with a lid. Okay, so they can exchange energy but not matter. Okay, and an isolated system is the most restrictive. It's where neither matter nor energy can be exchanged. In real life, this doesn't exist because eventually the energy will leave. But if you have like an insulated thermos, that would be a good, I guess, close example. Okay, it does a good job preventing energy from leaving. That's why the coffee can stay warm for a long period of time. Okay, so those are the 3 different types of systems. Typically, we'll be working with closed systems when we talk about chemical reactions. So if you want to put a star next to it, just know we'll be talking about closed systems typically where energy can go in and out, but the matter will stay inside of the system. Okay. All right, any questions on the 3 types of systems? Okay, so in thermochemistry, there are 2 terms that are super duper important. I do want you to write it down. Heat and temperature. Okay, and there's a difference between the 2. In everyday life, we kind of use these terms interchangeably. But in chemistry, we got to make a distinction between them. Okay, so the easiest way to think about heat is basically how the energy moves. Okay, so how energy moves. It always requires 2 objects. Okay, so heat is talking about 2 objects. How is energy moving between 2 objects? All right, now the key thing to remember, this will come up a little bit later, is energy always goes from a hotter object to a colder object. Okay, in chemistry, there's actually no such thing as cold. It just means that object has less energy. It's so high energy versus low energy. And energy will always go from the higher object to the lower object. Okay, so when you are doing your FRQs, when we're talking about heat, never use the word cold. You'll actually get points marked off for that because, again, in chemistry, and if you take physics as well, there's no such thing as cold. Cold is just relativity. It's just basically something that has lower thermal energy. All right, temperature is different. Is temperature always has to do with one object, and it's basically how fast the molecules are moving. So how fast the molecules move. Okay, and it has to do with one object. Okay, so that's the difference between the two. Heat is energy moving between two objects, and temperature is just how much energy one object already has. Okay, so if we were to use a quick scenario, usually we talk about the weather, right, when we talk about heat and whatnot. So let's just say that it is a very hot day, right, and then this is you. Okay, you don't need to draw this picture, by the way. And then there's air molecules around you. Okay, your body temperature, so your T is, I'm going to use Fahrenheit, is about 98 degrees Fahrenheit. Okay, and let's say the air temperature around you is about 100 degrees. Okay, so it's a very hot day. So that's temperature. Now heat, okay, the the variable for heat is Q. So the Q would be the heat, the air temperature giving energy to your body, because the air molecules have more energy than your body. The air will give energy to you, and that's why it feels hot. It's because the air molecules are giving you energy as they collide with your body. Okay, so that's basically the difference between T and heat. All right, any questions on the difference between heat and temperature? I know it's a lot of definitions right now. We'll get into the actual stuff in a second. All right, so let's move on. We're going to skip this. Skip, more skip. Okay. All right, so before we start the actual problems, let's talk about last two terms. When a system absorbs heat, it's called endothermic. Okay? When a system absorbs heat, it's called endothermic. So the previous example we just talked about, where you are outside, your temperature is 98 Fahrenheit. The air temperature around you is 100 Fahrenheit. Okay, energy is going into your body from the air. If your body is the system, we call this endothermic. Okay? Because the system is gaining energy from its surroundings. Okay, but let's say opposite case, you walk into a freezer. Okay, your body temp, hopefully, is still 98 degrees Fahrenheit, because if it's not, you're probably dead. And then the temperature of the freezer is, let's say, 30 degrees Fahrenheit. You have more, your temperature is higher than the air around you, so you will start giving away energy. Okay? And that's when you would be exothermic. So that's kind of the difference between the two. Endo is when the system absorbs energy. Exo is when the system releases energy. Okay, so we're going to draw something called a heat diagram, and we're going to draw arrows to basically describe how the energy is moving. Your pictures don't need to be very beautiful. They can just be kind of whatever, but as long as they get the point across. So an ice cube melts on a hot day. So we're going to I'm going to draw a table, and we're going to draw our ice cube. Okay. And then it is a hot day, so I'm going to draw the sun. Okay, again, your picture does not need to be as beautiful as mine, just as long as it gets the point across. Okay, so if an ice cube is just sitting out there in the sun, it is in contact with a couple things, right? It's in contact with the air molecules primarily. It's also in contact with whatever surface it's on, so on and so forth. Okay, so when we're trying to draw the heat flow, we first need to look at the temperatures of the individual objects. So if we look at the ice cube, right, it's frozen water. So it's the T is probably going to be around 32 degrees Fahrenheit, right? And then the air molecule, right, it's a hot day, so it's probably going to be greater than 32 degrees Fahrenheit. Okay? Make sense so far?
Yeah.
Okay, so because the air molecules have more energy than the ice cube, what's going to happen is the air molecules are going to give energy to the ice cube. Okay, so this is our heat diagram. We're drawing energy as arrows going into the ice cube. All right, now the ice cube is the system. So is this an exothermic or endothermic process? Endothermic, correct. Okay, because the ice cube is absorbing energy. Okay. Okay, so let's look at 611. So firework explodes in the air at Disneyland. So I'm gonna draw my Disneyland castle, the worst place on earth, with overpriced Dole Whip and kettle corn and churros and anyway.
Wait, for number 12, you didn't say which one was the system.
Yes, I did not. Okay, so the firework explodes and the air around the firework is the system. Okay, so we have air right here. Fireworks go off at 9 p.m., so it's kind of cold. So let's say it's like a 60-degree day, 60 degrees Fahrenheit. The firework is basically a bomb, so temperature is greater than 60 degrees Fahrenheit. So let's look at how the energy moves. Okay, energy is going to move from the firework into the air around it. If you got something like that, you're good. Obviously, your picture doesn't need to look like mine, but energy is going from the firework into the air around it. Okay, so the key thing here is that the air is the system. So if we look at the air, is the air absorbing or releasing energy?
It's absorbing.
It's absorbing. Correct. It is endothermic. Okay. Typically, people look at the firework and they say, "Hey, it's releasing energy because basically a tiny bomb." So they say it's exo, but again, it depends on what the system is. So always look at what the system is. All right. 612 is we got a freezer. And then we got a water bottle in there. So I'm going to draw my little water bottle. Okay, temperature is about, I don't know what water would be. Let's just say it's 50 degrees Fahrenheit. And if it's a freezer, it's going to be less than 32 because it's trying to freeze it. Okay, so that means that the water bottle has more energy than the air around it in the freezer, right? So energy is going to leave the water bottle into the air around it. So you should get something like that. And you don't need to write these numbers. It's just me kind of trying to explain it to you with numbers, but as long as you get the general idea, you're good. Okay. All right, now, there's a problem with this problem. Anyone catch it?
There's no
I
system.
did.
Yeah, there's no system. I didn't tell you what the system is, right? So you cannot say if it is exothermic or endothermic because it depends. And that's the point with this problem. You always need to define the system if you're going to talk about exo and endo, because let's say that the system is the freezer. If the freezer is the system, is this exo or endo?
Endo.
Endo, because the freezer has to absorb energy from the water bottle, even though it's a very small amount. Okay, but if we say that the system is the water bottle,
It would be an echo.
correct, it would be exo because the water bottle is giving energy away to the freezer. Okay, so just keep that in mind. You always need to define what the system is. Yeah, what's up? Okay, so we are going to be talking about energy in terms of something called enthalpy. I want you guys to write this down. The symbol for enthalpy is capital H. Okay, enthalpy. It's not entropy. We're going to talk about that unit 13. Yes. Entropy is the reason you die. Everything breaks down.
I watched like a 30-minute long movie
About entropy? All right, so enthalpy is something called, is basically, the variable we use to describe it is capital H, and you can just kind of think of it as heat, okay? It tells us whether the system is gaining or losing energy, if it's exothermic or endothermic. Okay, so what we're going to have a lot is we're going to have like a chemical reaction. So for example, I'll have, I don't know, you'll have something like this, H2O2, and you don't need to write this down, produces H2O, and then at the very end of the equation, it'll tell you delta H, so change in enthalpy, and then it'll tell you either a positive or a negative number. And that's going to tell you if the system is endothermic or exothermic, if the chemical reaction releases or absorbs energy. All right, so with that being said, I do want you guys to write this down. If delta H is a positive number, it means the chemical reaction is endothermic. That means it's going to absorb energy from the surroundings. Okay, and if you have a delta H that is negative, that means the chemical reaction is exothermic. It's going to release energy. Okay, now there's a couple other things that we can add on to this just to help us understand it a little bit better. So if its delta H is positive, that means the system absorbs energy, right? It's basically taking energy away from the things around it. Okay, and so let's say that you are holding this chemical reaction in your hand. If it was endothermic, that means to the system, to the surroundings, so you're the surroundings now, it's going to feel cold. Okay, because this chemical reaction takes energy from its surroundings. So it's stealing energy from you. If it's taking energy from you, it's going to feel cold to you. So a good example of an endothermic reaction is like a chemical ice pack. If you guys have ever used it, you have to pop that bubble in the middle, you shake it, and it gets cold. It's because it starts an endothermic reaction and starts taking away your energy. That's why it feels cold. Okay, but if the delta H is negative and it's exothermic, to the surroundings, okay, it's going to feel hot because it is giving away energy to you. Okay, it's giving energy to you. Best example of this is like a firework or a bomb. Okay, so it tells you that you have a container with ammonium nitrate, water, and some unreactive gases. And then it tells you the ammonium nitrate and water react. Okay, so that's our reaction. We got ammonium nitrate, so NH4, NO3, because everyone knows their polyatomics, right? Plus H2O, and it makes some products. Okay, it doesn't tell us specifically what it is, but it's not important. That's the information that we have. Okay, ammonium nitrate and water react, and the system contracts, or the container contracts. And this is where we have to use our knowledge of gas laws in order to finish up this equation. Okay, so it's made up of these things and unreactive gases. So let's think about it. If something contracts, it's getting smaller, right? If something size changes, what variable about gases are we talking about? Volume. Yeah, so if the container contracts, okay, if something contracts, that means that the volume is changing. How is the volume changing? Going up or down? It's going down. Volume's going down. Okay, so that's what this is telling you. If something contracts, the volume goes down. Now, we're talking about thermochem, right? So more important thing that we're talking about is the temperature. So let's see if you guys remember. If the volume goes down, what's happening to the temperature? Temperature's going down. Temperature's going down. Because remember Charles' law, V1 T1 equals V2 over T2. They have the same relationship. Okay. Okay, think about it this way. You put a balloon in a freezer, what happens? Okay, nobody's ever done it. But you put a balloon in a freezer, it's going to get smaller. The temperature goes down, the volume goes down. So if the container is contracting, that means the temperature is going down. If temperature is going down, what's happening to the enthalpy? Is it positive or negative? Yes, it is losing energy. And so that's part A. It's identifying that if the container is contracting, the temperature is going down. If the temperature is going down in the system, that means the system is losing energy. Okay, so this will be our answer for A. Okay, change in enthalpy is negative. And then how do you know? You can say that if the gases are contracting, that means it's getting colder, or the temperature is decreasing. If the temperature is decreasing, that means the enthalpy is going to be negative. Sorry, I made a mistake. So let me just rewind real quick. So this is our container, right? We have our ammonium nitrate. So this is where our reaction is happening. Sorry, I made a quick mistake. Okay, so this is where our reaction is happening, right? And then there's gases. There's these unreactive gases up here. That's what this question is telling us. Everybody good with that? Sorry, let me erase some stuff so that we can see it. So our reaction is happening here, and then there's unreactive gases. the container is going to contract. That means the gases right here, the temperature of these gases are going down. That part, you guys good, right? Okay. If the temperature of these gases are going down, that means that the reaction is taking energy, from the gases. That's the only way for the gas temperature to go down. And so the enthalpy is positive, my bad, because the system right here is gaining energy from the gases. I apologize. I haven't looked at this in a year, so I totally goofed up there. My bad. So just to reiterate, since the gases get colder, the energy is being taken by the chemical reaction. That means the chemical reaction is positive. It's endothermic. My fault. So let's take a look at 614. Basically, it tells you that you got a cylinder with this system. So this reaction is taking place inside of a cylinder. Okay, that's what's happening. It says it's perfectly insulating, so we're not assuming energy escapes. This is going to be a closed system. And then the spark causes butane to combust, and it forms carbon dioxide and water, and this is the reaction. First question, is this going to expand or contract? All right, so very simple. The key term right here is that this is a combustion reaction, right? If you guys remember, what's the most common form of combustion that you guys are familiar with?
Fire.
Yeah, fire. Some type of fire, explosion, whatever, right? And if there is heat like that, what happens to the container that it's inside of?
It increases in volume.
It's going to increase in volume, exactly. So this is going to expand. Okay, and your reasoning would be because it's combustion. Okay, that's one way to look at it. There is actually a different way to look at it, and I'll talk about that. Okay, so it expands because it's combustion, but also, let's take a look at the chemical equation. If you look on the left side of the equation, there are 15 moles of gas on the left side, right? Do you guys see that? There are 15 moles of gas on the reactant side.
And there's 18.
Exactly, there's 18. So which side has more gas?
The
Product side, right? If there's more gas, it's going to take up more space. And so that would be the other reason. The other reason is because there is more gas on the product side. All right, any questions on A? So those are the two explanations that you can give. I wanted to talk about the moles of gas because it's just another way to think about it and something else for you guys to look for in these problems. Okay? All right, so for part B, will this be endothermic or exothermic? Well, we talked about volume, we talked about explosion, right? So obviously this is going to be exothermic. The system is going to release energy. And if it is exothermic, the enthalpy will be negative. Exactly. There you go. All right, so let's talk about something called enthalpy of reaction. Now, we talked about how when we have a reaction, we have an enthalpy at the end, the delta H, right? Now, just know delta H is always equal to the enthalpy of the products minus the enthalpy of the reactants. Okay, delta H is products minus reactants. Okay, and essentially what that's telling us is it's telling us if this energy is a reactant or a product. Okay, so let's say we have this reaction right here. It's the combustion of a hydrogen gas. And then if you look, the enthalpy is negative 483 kilojoules, right? Basically what it's telling you is that energy here is a product. You are making energy in this reaction, which makes sense, right? Because you react it, energy leaves the system. That means you are making energy using these chemicals right here. Okay, but if you had a delta H that was positive, if you had a positive delta H value, that means that energy is a reactant. Okay, so that's essentially what this is telling us. The delta H, the sign, if it's positive or negative, is telling you, is energy a reactant or is energy a product? Are you using energy to start the reaction, or are you making energy in the reaction? That's what it's telling you. But let's go into the stoichiometry portion. Okay, so hopefully you guys can have this up on your screen. That way you can see the equation a little better. But here we have our equation, and we have the enthalpy for the reaction. Okay, so we're getting into stoichiometry now using the balanced equations. All right, so the question. So let's just jump right into it. Question A is asking what's the enthalpy for the reaction per mole of CO2. Okay, so per mole. Now, if you guys remember, what does per mean in terms of numbers? What number does per mean? 1. Yeah, per always means 1. That's why it's miles per hour, right? Miles in 1 hour, so on and so forth. So it's asking for the enthalpy change per mole of CO2 in this reaction. So we're going to start with 1 mole of CO2 as our starting value. All right, so we got 1 mole of CO2, and we're going to try to figure out enthalpy. Okay, so what we're going to do is we're going to set up a fraction, and we're going to try to cancel out moles of CO2 here on the bottom. Okay? Now, if you look at the balanced equation, what's the coefficient for CO2? 4. Good. So we got 4. And then we are looking for the enthalpy change. And if you look at the enthalpy change, it is negative 3120 kilojoules. So we can just put that on the top. Okay, and all we got to do is solve. Okay, so this question is just showing you that enthalpy is just like another thing in the chemical equation. Okay, you just need to set up the ratio using the coefficients and the delta H, and that will give us our answer. Okay, but the phrasing is actually super important, so that's what I want to talk about next. Okay, so this is going to give you negative 780 kilojoules. So this is going to be our answer. All right, so let's talk about the phrasing, because the phrasing can get a little bit confusing here. So let's look at this negative number. So this negative sign, I want you to make a quick note. This negative sign means released. Okay? So whenever you are answering questions in terms of enthalpy, you're going to always want to phrase it a very specific way. You want to write either just negative 780 kilojoules, or you're going to write 780 kilojoules released. Okay. Do not ever write negative 780 kilojoules released, because it's going to cancel each other out. You're basically saying 780 absorbed then, which would be incorrect. So don't put this one. If you put a negative, don't write released. If you write released, don't put a negative. Okay? If you put them together, you're kind of going backwards, like a double negative. Okay, so just pick one or the other. I would recommend just write this, just because it's easier, less work, right? Less writing.
After negative 780 absorbed.
You could. You could if you want. All right. Any questions about that? Just be very careful, because it's a very common mistake and people just lose points for no reason. They do all the work correctly, and at the end they just do too much and they write negative 780 kilojoules released and they get it wrong. Okay. Part B. Do the reactants or products have a higher enthalpy under these conditions? Now, earlier we said that the delta H is always the H of the products minus the enthalpy of the reactants. Okay. So we're trying to figure out if the products or the reactants have a higher enthalpy. Okay, and this is pretty simple. If you look at the delta H right here, it's a negative number, right? Which number has to be bigger in order for us to get a negative for the delta H? The reactants, because you're subtracting it. So here, it would be reactants. Okay, the H of the reactants is higher. Okay, and then you would use this equation to prove that. Yeah. All right, any questions on B? Okay, let's move on to C now. C is going to touch on another characteristic that has to do with different states of matter and energy. So let's take a look. The question is saying if liquid C2H6 was consumed. So if you look at the reaction right here, we're using gas C2H6, right? But the question is just saying, hypothetically, if we used liquid H2C6, if we swap this out, instead of gaseous, would you expect delta H to increase, decrease, or stay the same? Okay, so in order to solve this, we need to actually think about what the molecules are doing in a liquid versus a gas. Okay, so let's write that down somewhere. We're going to look at the liquid versus a gas. Okay, and what we need to figure out first is what state of matter has more internal energy in and of itself. And the answer is going to be a gas. Okay, so gases typically have more energy or more internal energy than a liquid. Okay, easy way to think about it is if you boil water, right? When you're boiling water, you're heating up the water. You're putting energy into the water, and once the water molecules get enough energy, they vaporize and turn into gas. So the gas molecules have a lot more energy than the liquid water does. Okay, so gases have more energy than liquids, and then liquids have more than solids, yeah. Exactly, yeah. All right, so since gases have more internal energy than a liquid, if we switched out the gas for a liquid, let's look at the enthalpy of the reactants. Is the enthalpy of the reactants going to go up or down? Do we have more energy or less energy? Yeah, less energy. If we switch out a gas for a liquid, the internal energy, energy of the reactants is going to go down. Okay, so the H of the reactants is going to go down, and the reason is because liquid has less internal energy than gas. Okay. So far, so good? Okay, one last step. The question is not asking you about just the H of the reactants, they're asking about the delta H. Now we know delta H is equal to the H of the products minus the H of the reactants. Okay. Okay, so if we change the gas for a liquid, the delta H is going to get smaller. So that means that this number is going to get smaller. Okay, so if this number gets smaller, what's going to happen to the delta H? Yeah, delta H is going to get greater. Okay, so delta H will increase. Okay, so that's going to be actually our first answer. There's going to be a second part we do need to talk about, but delta H will increase, and these are the reasons why. So far, so good? Okay. However, the question is asking not about the delta H, it's asking about the magnitude of delta H. And so it's asking for the absolute value. So basically, is this number, apart from positive or negative, going to get smaller? And the answer for that, the magnitude of H will decrease. Okay? And that it's because of the number scale. If we look at the number scale, let's say we're at 0, and we said this is 3120, negative 3120, right? If delta H gets smaller, H will increase. If it's increasing from negative, that means it's going to go somewhere here. Like, let's say, for example, it's like 2,000. If it's 2,000, yes, or negative 2,000, yes, it is a bigger number, but the magnitude is smaller. So just be very aware of that word magnitude. That's why I'm talking about this. Because if the question was asking, do you expect H to increase, decrease, or stay the same, you would say H would increase. But since it's asking magnitude of H, you have to say that it will decrease. So just be very careful with the terminology. It makes a big difference, especially when you're working with negative numbers. Okay? So So that's why we're doing this problem, so that you're aware of that term magnitude. It's just basically the size of the number independent of the positive and negative sign. Okay, so we're going to do one Stoich together, and then I'll have you guys try one on your own. So let's do 616. First thing we're going to do is identify, is this exo or endothermic? We're going to look at delta H. What is it, exo or endo? Delta H is positive or negative? Positive. If it is positive, it is endo. This is endo. Okay, it's our first day looking at it. Just make sure you remember that. Okay, delta H is positive, which means it's absorbing energy from the surroundings. That's what the positive means. All right, part B, calculate the amount of heat. So if you're looking for heat, you are looking for Kj transferred when 10 grams of nitrogen gas reacts with excess oxygen, basically in this system. So our starting number is 10 grams of nitrogen gas. So we're going to start doing our dimensional analysis. 10 grams nitrogen gas. First thing we want to do, since we are working with, we're looking for energy, we have to turn it into moles in order to use the chemical equation. So molar mass of N2 is 28 grams. So 28 grams per 1 mole of N2. And then we're going to set up another fraction. This time we're going to convert moles of N2 into Kj. So see if you can set up this second fraction. I'll give you like 30 seconds to do that, and then I'll show you what it should be. See if you can set up the second fraction using the equation. Alright guys, so if we look at the balanced equation, for N2 the coefficient is 1, so every 1 mole of N2 produces 67.6 kilojoules of energy. And so that is going to be your second fraction. So we plug that in, 10 divided by 28 times 67.6. That'll give you 24.14 kilojoules. Okay, and if you really want to add absorbed, you can. Alrighty guys, so I got the answer for part C up on the screen for you. Starting value 200 kilojoules. Use the coefficients from the balanced equation, 2 moles of NO2 for every 67.6 kilojoules of energy. And then molar mass of NO2 is 46. You just plug and chug and you're all done.